So in the last video, we were talking about correlation coefficients, and we left off with this, returning to this example of the population of Portland, Oregon. I've gone ahead and entered all this data into my stat editor. Whoops, where did it just go? Stat editor, there it is. And what I want to do is just show you how to find the correlation coefficient once we do the regression. So I've got my data entered. Then I need to actually do the regression. So we go to StatCalc. Number 4 is linreg. And this is L1, L2. And then we'll save it as Y1. And there it is. So there's our linear regression function. And to get to the correlation coefficient, let me go back to the slide where that has the directions so you can see this. So it's var's statistics equation. So I go to vars for variables, and then number 5 is statistics. Scroll over to equation, and then number 7 is the correlation coefficient. So you select that, then hit enter, and it brings up this value, 91657. Let's write that down to 4 decimal places, so that will be 9166. Okay. So that's how you find your correlation coefficient. And then in regards to the critical value, this was how many data points? Well, we had 1, 2, 3, 4, 5, 6 data points. So then we would go to the critical value chart and look up 0.811. And 0.811 is definitely less than 0.9. I forgot what it was, but it was 0.9. I think it was 166. Is that right? Well, I've totally lost it now. Anyway, 917. Okay. Definitely less. The critical value is definitely less than correlation coefficient. So we can be 95% confident that population and time are linearly correlated variables in Portland population model. Okay. Now, as you see in this slide, which has the answer, this is written in terms of the absolute value. Now, that doesn't accomplish much in this case because it's already a positive correlation. If it had been a negative correlation, then this absolute value you would have seen the use of it a bit more. But just the point is just so you don't have to think about whether you're on the left or the right. Okay. All right. So there's an example of linear correlation. And then to kind of review all the error analysis quantities that we've looked at, let's go through each of them. So we talked about model error, which is actual value minus predicted value. We also have a concept called percent error. I'm not sure we've used that actually yet, but I'll go ahead and define it. The percent error is the actual minus predicted divided by the actual, and then we convert that to a percent. So this gives you the percent error at any given point. Okay. Then our overall regression model, we have the SSE, of course, and the average error, and here are your formulas. Actually, this is a slightly different formula, which is also useful. There's more than one way to do this. Maybe we should go back and calculate an SSE using resid. Let me set that up and we'll do it. Okay, so as I was saying, I wanted to calculate the SSE for this Portland model using this alternate method. Now, I just want to point out we have already done this. We calculated the SSE using the standard method where we did L1, L2, L3, and L4, and then we did sum of L4 squared, right? And we got, I think it was like 6,666 point something. Actually, we can just scroll back and find it. There it is. Okay. Now what I'm going to show you now is another way to do this using resid. And to be honest, this is easier. So you might want to know both methods. The downside to the resid method, actually there's not really a downside. Well, first of all, what is resid? What is a residual? Well, a residual is just the model error. It's just another name. Actually, let me write that up here. So this is the same thing as a residual. Okay. And the calculator, what we've been doing is actually computing the model error explicitly, actually doing actual minus predicted. But the calculator has a button to do this in one fell swoop called the resid button. And let me show you how this works. So I already off screen, I entered my data for the Portland population model. So there's my data entered already. And then I'm going to do the regression. Number 4. Now, of course, you have to do the regression. Otherwise, none of this will work. Okay, so there's my regression line. And if I want to get the SSE of this, I can go directly to this command, this sum resid squared command. Because what that's going to do is it's going to calculate the sum of the residuals squared, and the residuals are the model errors, and that's the SSE. So I don't even have to do any of this in the, considering that you've already entered your data in the stat editor, you don't have to do any more work in the stat editor. And here's how that looks. So first of all, I go to sum. So that's second stat, and math, it's number 5. And you may have seen there that you might have seen resid on the screen, but so let me go back to it. So I go to second stat again, and then right there, number 7 is resid. So just click number 7, or scroll down and click resid, and then hit the squared button, close your parentheses, and hit enter, and there's our SSE. So notice I didn't have to do y1 of L1, I didn't have to do L2 minus L3 or L4. I could just go directly to computing the SSE. The only downside to this, I think, is that if you only do it this way, you kind of forget what the function, the SSE, like where it comes from. And kind of breaking it down into steps will hopefully help to teach you what the function is made up of. And then once you've done that a few times, you can sort of shortcut it and go to this resid process. All right, so anyway, there it is. There is our SSE. And then to calculate the average error, we would take that SSE, divide it by the number of data points, and then square root all of that. Okay. The average error, we've talked a little bit about that, and we haven't talked really about why we have it. So let's do that. Let's talk about what the point is for the average error. So the point of the big use of the average error is that, as it says here, it's directly comparable to the data. The problem with the SSE is the SSE is in squared units. Whereas the average error is not. The average error is not in squared units. So we can directly compare it to the data values used to generate the regression model. And then thusly, we can use the average error to get a feel for how closely the model fits. In terms of the Portland model, the average error is 33.33 thousand. And that represents a significant error relative to population levels. We can actually compute the percent error, and I mentioned that on the previous slide for this, for these two values, 583 and 366. Let me go back to the data to show you why I'm using those two. So there's 583 and there's 366. So that's the highest and the lowest population values. Okay. So our relative error ranges between 5.7% on the low end and 9.1% on the high end. Continuing our discussion of using the model once we've done the regression, I need to define two important words, interpolation and extrapolation. For a set of data points, suppose A is the smallest of all the inputs and B is the largest of all the inputs, and a model has been found to fit the data. So basically we have some data set and it starts over here and it ends over here, and then we've got all our points in here, and then we found a linear model. It doesn't have to be linear, but let's suppose it's a linear model, you know, that approximates our data. Okay. To interpolate is when we use the model that we found to predict values between A and B. So let's suppose that we have those data points right there, those 6 data points. If I was interested in knowing, let me get a different pen here. Let's suppose I was interested in knowing this value, or the value associated to this input, which is not one of our data points, right? It doesn't look like it corresponds to one of the data points. Our model would put us right there, right? That's an interpolation because this point that I'm focusing on is between A and B. Interpolation is generally pretty safe with a regression. The other thing that you can do is you can do what's called extrapolation, which is when we take a value that is outside of the range of the data set, or the domain of the data set, I guess. So for example, out here, so this value, let's say C, is larger than the largest value in our data, and so the model will give us a value. The model will give us a predicted value, but it's basically we're forecasting, we're foretelling the future here, or trying to, and that's always kind of risky. Extrapolation, and that's an example of extrapolation. You're on less statistically solid ground when you extrapolate than you are when you interpolate. Okay, so up next, let's take this Portland model that we've been working with and use it a little bit more. Specifically, let's talk about the population in 2017. That's an extrapolation. So I'll bring in my model up. Let me clear all that. And this will be vars, yvars, function, y1. And we want to know the population in 2017. And our model began, I'm gonna be lazy, and since I don't want to do math, well, I guess I'm doing math, aren't I? But I don't want to do arithmetic. I'm going to just type in my input like that. Oh, you know what? Actually, I shouldn't do that, should I? Because I forgot. My regression is calendar year. I almost made a mistake there, but my regression is calendar year, so I can just directly type in the calendar year. That would have been, what I was going to do would have been for an elapsed time model, but that's not what we have. All right, so there's our population, 588.48, supposedly. I'm about out of time in my video, so I'm going to pause this and then we'll restart in the next video and finish these two examples.